Okay, welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 6 from the Statistics S1 International A-Level Edexcel October 2019 exam. And this question here is about normal distribution. It says a machine cuts wood into pieces. The lengths W meters of the pieces produced by the machine are normally distributed with a mean mu meters and a standard deviation sigma meters. Alright, so first of all, we know that the lengths, they've called that W, are such that they are normally distributed with a mean, which we don't know, so they've kept it as a mu, and a standard deviation, which is sigma. I'm not very good at drawing sigma. Okay, so this is the standard deviation sigma, so we always write the variance in this bracket, like this. When you, in this notation, you have the mean and the variance. So we know the variance is the square of the standard deviation, so you write sigma squared to denote that's the variance. Okay, they've told us two bits of information. They've said that the probability that the length of wood is less than 3.968 meters is given by 0.1. So we'll deal with that first. They've also given us this probability that wood is between 3.968 and 4.026 is 0.75. Let's deal with this first. And this was actually what one of the requests was on the channel for about this question. So let me just go through that part with you. Okay, so I've drawn here, well, I've copied here, a normal distribution bell curve, right? So drawing one of those is useful. I just copied one here. So here we have the normal distribution, right? This is what normal distribution looks like. When something is normally distributed, this is its, the shape of, you could say, the frequency table for it. So we've got W, and we've got what's called the Z values. What we're going to do is we're going to deal with standardizing the Z value, the length values, such that we have, the mean as 0 and the standard deviation as 1. Okay, because the table of values that we've got to deal with, which are here, they are for the bell curve like this, where the mean is 0 and the standard deviation is 1, and then these values in here apply. Okay, these values apply. So what we have to do with is we have to deal with, first of all, the mean here we don't know. Okay, the mean is mu. Alright, they've told us that the probability that the length W meters of the wood is 3.968 is less than 3.968 is 0.1. Now, the probability is given by the area under this curve. The area under this curve gives the probability of something. And if the probability that the length of the wood is less than 3.968 is 0.1, okay, then we know as the total probability of anything is equal to 1, the total area under this curve is equal to 1. So we know that 3.968 must be somewhere over here. It must be somewhere in that region there, because the probability of the length being less than that is a small area, 0.1. Okay, so this area here is 0.1. Okay, it can't be over here somewhere, because the area to the left of it is going to be more than 0.5 is on this side. Okay, so it has to be somewhere on this side where the Z value is going to be negative. So this is 3.968. Okay, here the Z value, the mean is 0. For when you got Z, this place represents the mean is 0. This represents numbers which are less than the mean. So we want to find how many standard deviations below the mean this is, and that will help us to find out the value of mu and sigma in the end, alongside the information we can extract from this situation. So I can see this is representing now that the probability that the width is less, or the length is less than 3.968 is equal to 0.1. That's what represents it. Now, so we've got to find what is this Z value. I'll call it Z1. What is this Z value that corresponds to this? Now, what we know is basically we can see on the table what this Z value is. Okay, because the areas such as 0.1, 0.2, which are shown on this table here, like here you got the area 0.1, 0.15, 0.2, 0.3, 0.5, is that all these are on this table, which is on the top of the page, the small table. These are all areas. This is P stands for the probability of the area. This is the Z value to which this is the area to the right of that Z value. So the table on the top of the table on the top gives you the area to the right of that Z value. So for example, if the area is 0.5, okay, then that means the Z value is 0, which is here, right in the middle. That area is 0.5. If the area, for example, is 0.4, okay, then the Z value is 0.2553. So this area here would be 0.4, and this would be 0.2553, so on. Okay, that's how that works. So let me just copy that table onto our page. It's a bit big. Make it smaller. Okay, so I've just taken the whole table just for you. I'm going to go through this in a bit of detail to explain, especially for the student that was asking about this. Now, so we know that this tells us the area. This is the area to the right of that Z value. Okay. Now, I know that the area to the right of this Z value is 0.9. We don't have 0.9 here. Okay. We don't have 0. This is the area to the right of that Z value. The areas start from this side here, where you got 0.5, then 0.4, then 0.3. So what we have to do when we're dealing with areas like this, we've got to think about the symmetry of this normal distribution curve. So I'm going to think about that same area, but on the other side of the diagram. So I'm going to draw a line like this. Okay, but on the other side of the diagram, over here. Now, this is symmetrical. So this area is also 0.1. This area is also 0.1. So the Z value I find here, okay, this is the negative version of that Z value. Okay, this is the negative version of that Z value. All right, so what I can do is, I can find that Z value by looking at the graph. I can see, looking at this, we're looking for an area of 0.1, which is this area here. And that's the Z value that corresponds to it. So the Z value on this side here is 1.2816. However, what are we looking for? We are looking for the Z value over here, which is the mirror image of this. This is 0. Okay, this is where the Z value is 0. The mean is 0. We're making this. We're basically standardizing these scores into the scores where we have the Z values where the mean is 0 and the standard deviation is 1. So that this means basically that this score here is 1.2. What was it? 1.2816 standard deviations above the mean. So what we have here is 1.2816 standard deviations below the mean. The symmetry. So we can say that the Z1 value here is negative 1.2816. That's the reason why it's negative. Okay, because we know the area to the left of this is small. To the left of this, because it says less than, is small. So the Z value must be somewhere to the left of the mean, below the mean. So the Z value tells you how many standard deviations above or below the mean we are. If we're below the mean, it's going to be negative. If we're above the mean, it's going to be a positive Z value. Okay, because when we standardize the scores, we make them into Z values, where we make them into something where the mean is 0 and the standard deviation is 1. Then we can read off the areas correctly from the tables that we have, because those tables are designed for when you have standard deviation of 1 and the mean of 0. Okay, so I hope that's clear why Z1 is negative here instead of positive. All right, if it said the probability that W is less than 3.968 is equal to 0.9, then that would be the answer. Or if it said the probability that W is greater than 3.968 is 0.1, then Z would be 1.2816. Okay, but here it's less than, this value is 0.1, so it's this small area over here. Okay, so now what we can do is we can use the fact that we have this formula for standardizing the scores, which is Z equals X minus mu over the standard deviation. So X minus the mean of the standard deviation. So here we know Z1 is minus 1.2816, and we know what X is. It's 3.968 minus, now what we don't know is the mean and the standard deviation. So we've got something where we have now made an equation which involves both of them. Let me just multiply by sigma. So minus 1.2816 times sigma, I'm trying to draw it so it doesn't look like a 6, equals 3.968 minus mu. So that's like one equation we formed from this information over here. Now we got another piece of information. Okay, the other piece of information they've told us is the probability that W is between 3.968 and 4.026 is 0.75. Okay, so let's just take this and let's deal with this a second time now. So we've got here the probability. We got, say this is your 3.968. So we've got W values here. Got our W values of 3.968. We know that this area is 0.1 already. We found that. We know that from the first part of the question. Now it says between 3.968 and 4.026, the probability is 0.75. Now what I know is this section here, what's left, remember this is, the whole probability is 1. So half of this bell shape takes up 0.5. So this must be 0.4 here. Between here and here is 0.4. All right, so that's, we got another 0.35 left between these two. So another 0.35 left. So we can go up to somewhere over here. That's 0.35. So altogether that makes 0.75. So this value of W is over here somewhere, 4.026. So we know for sure that this is somewhere above the mean. This is somewhere above the mean. Okay, it's going to have a positive Z value because we can deduce from this that 0.85 of the area. We can say, for example, this shows that the probability that W is less than 4.026 is equal to 0.85. We can say that from this because there's 85% of the area to the left of it. You have 0.1 and then 0.75. We can also say, which means that the probability that W is greater than 4.026 is equal to 0.15. Okay, 0.15 is the probability that the area is greater than 4.026, and that will help us because we can use the same table here. In fact, we can use the row just directly above the one we used first. That's a probability. Okay, that's a probability. Okay, and that's the area to the right of this Z value. So the probability that something's bigger than the Z value is 0.15. So we can see, or we can deduce from that the Z value for this is going to be 1.0364 positive, because it's above the mean this time. 1.0364. So we can deduce from this, let's call this Z2, that Z2 is equal to 1.0364. So now we can come up with another equation, just like we did before, using the standardized scores. We now remember that Z is equal to X minus the mean over the standard deviation. So we can use that. We can say 1.0364 is equal to the score, which we know is 4.026, minus the mean, which we have to find, over the standard deviation, which is what we have to find. Okay, so we have now a second equation. From this, we can deduce a second equation, 1.0364 times sigma is equal to 4.026 minus the mean. So we can have these two equations together. Okay, so I'll write, this is equation 2 now. I'll write equation 1 underneath it. You have minus 1.2816 times sigma is equal to 3.968 minus the mean. So these two equations can be solved simultaneously. If I subtract these two equations, if I do equation 2 minus equation 1, I'll get these being eliminated and I'll get the answers. So let me just put this in the calculator and get it. So we have 1.0364 minus, so it's going to be plus, because you're basically going to be adding them together, plus 1.2816 So that gives me 2.318. 2.318 times the standard deviation, which is sigma, is equal to, and then these have to be subtracted. So I have 4.026 minus 3.968. Okay, make sure I don't make a mistake with typing them in. Okay, so that gives you 0.058, 0.058, and when you subtract them, they become 0. So we can find what our standard deviation. So standard deviation sigma is equal to 0.058 divided by 2.318. So therefore we can say the standard deviation is equal to this divided by 2.318, which gives us 0.02502. 0.02502. So we can say that's equal to 0.02502 to 3SF. That's the standard deviation. And we can find the mean. The mean is equal to, let's use this equation here. You can say it's equal to, if we do, it will be 4.026 take away 1.0364 times the standard deviation, which is 0.0250. Okay, so I'll take this last value here, and what I'll do is I'll do 4.026 minus 1.0364 times the last answer, and that gives us 4.00006. So that's 4.0000, goes on like that. So we could just call that 4.00 if you want, or even 4 I guess would be okay. So we can say that the mean is equal to 4.00 to show us an not exact value. So we can say the standard deviation is equal to 0.025 3SF, and the mean is equal to 4.00. So there's the answer to part A of this question. We set up a pair of simultaneous equations using the information given. Okay, in this particular question, we only had to deal with the table, the small table with the areas, which are exact values almost, and you know that it made life easier there. We should use this table if we can. Okay, it's very important. That is, you know, for us to know that. If we can't use the table, then we have to go to the table below it. All right, now for part B. And now for part B. We are told here that a second machine cuts wood into logs. The lengths L centimeters of the logs produced by the second machine are normally distributed with L being such that it's normally distributed with a mean of 30 and a variance of 0.5 squared. So that means the standard deviation is going to be 0.5. Okay, so that's the information we extract from there. Then it tells us about outliers. As an outlier is a value that is greater than Q3, which means the upper quartile, plus 1.5 times Q3 minus Q1. That's the interquartile range. That's a standard kind of definition of a outlier. So the outlier is greater than the upper quartile plus 1.5 times the interquartile range, or it's less than the lower quartile minus, again, 1.5 times interquartile range. Now, log is selected at random. Given that the lower quartile, Q1, is 29.7 to 3 SF, find the probability that the length of this log is an outlier. Okay, so let's take our little table, not our table, our diagram, and try and figure this out. Look at the big picture from here. Now, basically, we have the mean over here, which is the same as, you could say, the median in normal distribution. That's the mean. Now, the lower quartile is a value. Let me draw this down here so that I've got some more space. Okay, the lower quartile is the value such that it is more than 25% of the data. So in terms of this table, let me just make that thinner. We could picture it as being somewhere over here, such that, so this is the lower quartile, Q1, which they've told us is 29.7. Okay, such that this area here is 0.25. That's the lower quartile. Okay, and the upper quartile is such that the area to the right of it is 0.25, because it's such that it's bigger than 3/4 of the data values. So it's such that it's bigger than 3/4 of the data value. So therefore, 25% of the data is above it, okay, or is greater than it. So you can say that the upper quartile would be over here. This is Q3, and this would be 0.25. Now, what we're trying to find is a probability that the length of the log that's chosen at random is an outlier. Now, the outliers are such that it's a certain value, which is the low quartile minus 1.5 times the interquartile range, less than this value here. So it's going to be something over here, and the upper limit will be something over there. Okay, so this is the lower limit. Okay, let me call this L1, the lower limit, and this is L2, the upper limit. Okay, so we're looking for basically the probability that something is in the region. Let me look at a different color slightly. In this region here, and also in this region here. These two probabilities, these two areas added together will give us our answer. That will be the probability it's outside the limits of the outlier. Okay, so I need this area and that area added together. Now, what I can do is use some symmetry here. The symmetry of this will really help us, because we know that this is normal distribution, so it's symmetrical to this bell curve. So we know the mean already. They told us what the mean is actually. The mean is given to us as 30. So this is definitely 30. So in terms of the values of L, okay, this distance here is 0.3. So this distance here must be 0.3 as well. Okay, because that's 29.7 to 30, 30 to 30 to Q3 is going to be 0.3. So this is going to be 30.3. So we can say that Q3, okay, because it's normal distribution, it's symmetrical. Okay, it's symmetrical. That means the Q1, which is the same as the median, Q2, sorry, which is the same as the median, okay, which is the mean. The median and the mean are the same in normal distribution. The distance is symmetrical, so that distance is the same as that distance. If that's 0.3, that's also 0.3, so that must be 30.3. Okay, we can say from symmetry. All right, because this is symmetrical. All right, so we don't have to do any calculations like finding Z values. We could do that. I guess we'll get the same answer, but we can use the symmetry of the curve. So Q3 is definitely 30.3. So therefore, the interquartile range, which we need, is going to be 30.3 minus 29.7, which is, I think that's 0.6, isn't it? Okay, just make sure. So we have 30.3 minus 29.7, which gives us 3/5, which is 0.6. Okay, that's the interquartile range. So therefore, we can say that the lower limit for the interquartile, for the what's called the outlier, sorry, lost the words there, is going to be 29.7 minus 1.5 times 0.6. So the lower limit of this is going to be, so we have 0.6 times 0.5, whoops, okay, that's 3/10, and you got to do 29.7 minus that, 29.7 minus that answer, that gives us 29.4. Yeah, 29.4. Okay, let's make sure of that. You have 29.7 minus 1.5. I think I put 0.5 times 0.6. Be careful here. 29.7 minus 1.5 times 0.6. That looks better, I think. Yeah, that's better. 28.8. Sorry about that. So that's 28.8. 28.8 in terms of the L value. Let me just move this down here because I want to show what to do to find the Z value. So what we need to do is we need to find the Z value for this. I'll call this Z1. This is for the lower limit, the Z value for the lower limit. Now, if I find this value of Z, okay, and then I'll be able to find the area to the left of this value of Z using the tables, and that will be my answer, which I have to multiply by 2 to give me the probability that something is an outlier, because that's a probability that something's lower than the lower outlier, and the probability that something's bigger than the higher outlier is going to be exactly the same, symmetrical. So if I find this area here, multiply it by 2, I've got my answer. So I need to find what Z1 is. So I need to standardize this score of 28.8. Okay, so I've got standardized score Z is equal to the score Q minus the mean over the standard deviation. That's our standard kind of formula. So we can say Z1 is equal to the X, which is we worked out is 28.8, minus the mean, which is 30, over the standard deviation, which is 0.5. Okay, so this will give me Z1. So we have 28.8. So 28.8 minus 30 divided by 0.5. That gives me minus 2.4, negative 2.4. So I want to find the probability that Z is less than negative 2.4, and I need to do 2 times that basically, but I'll do that in the end. All right, so that's the same as the probability that Z is greater than 2.4. Remember, we don't have values of Z that are negative in our table, so I have to focus on this, as this is 2.4. In terms of Z, this is 2.4. Okay, so I want to find this probability, but I'm not going to find, I need to use a lower table where I have the probabilities of what is to the left of the value. So this is the same as, this area here is the same as 1 minus the area that the probability of Z is less than 2.4. If I look at the table, I'll have, if I go to 2.4 in the table, I'll have this area here, all of this area here. What I need is the area to the right of it, so I'll do 1 minus that, and that will give me my probability, and then we'll get our answer. Okay, so that's going to be equal to, if we go to the table, look at 2.4. I've got it over here. Okay, this is 2.4 over here. Let's get rid of that. Okay, so I can take this and take it to where we want it. Where's it gone? It's up here somewhere here. Okay. So that's Z, and that is the probability what's to the left of it. Okay, so what we got here is basically the area all the way from here to the left of it. So we're going to have 1 minus this value, which is 0.9918. So we have 1 minus 0.9918, which gives you 41 over 5,000, which is 8.2 to the times 10 to the power of minus 3. So 0.0 0.082, 1, 2, 3. 8.2 times 10 to the minus 3, sorry, 1, 2, 3, that's right. So therefore what we have, okay, our probability, so the probability that something is an outlier is going to be 2 times 0.0082. Okay, this is, if we write this normally, that's 0.0082, multiply that by 2, and we get our answer, which is 0.0164. So that's 0.0164. There's the answer for this question. Okay, because what we found when we got this was this area here. We need to add this area to it. So as it's symmetrical, we multiply that by 2. Okay, so that's the answer to question part B of question 6. I hope that was clear. Thank you for watching. Other questions that you might want to ask from this or look at from this particular paper can be found in the playlist that should appear in this area over here. Other questions from S1 in general on this topic of normal distribution can be found in the playlist over here. You can subscribe to my channel by clicking on this link. Thank you for watching, and see you soon.